All right, let's talk about something incredible. Have you ever looked up at a giant skyscraper and just wondered, how in the world does that thing survive an earthquake? Well, it's not luck, and it's definitely not magic. It is some seriously brilliant engineering. Today, we are going to peel back the curtain on one of the coolest tools engineers have for this exact problem, the response spectrum method.
So let's just start with the most basic question, right? When the ground actually starts to shake, what's going on with a tall building? I think we all have this mental image of a giant hand just pushing it from the side. But the reality is so much more complicated and honestly, way more fascinating than that.
You see, that simple idea of a static push, it's intuitive, but it's just wrong. An earthquake doesn't push the building, it shakes the ground underneath the building. And that causes the whole structure to vibrate and whip back and forth in this incredibly complex, dynamic dance. Now, older, simpler methods, yeah, they kind of treated it like a big push, but that's just not going to cut it for a modern high-rise. To build safely, engineers needed a much, much better tool. And to solve that incredibly complex problem, they came up with something called the response spectrum method. Now, the best way to think about this is as a kind of elegant cheat sheet. It's a way to summarize how any building is likely to behave during an earthquake without having to run a simulation for every single possible scenario.
Okay, so what is a response spectrum? Well, at its core, it's a graph. And on the bottom, you've got the building's natural period. You can just think of this as its natural wobble speed, the time it takes for it to swing back and forth one time. Every building has one. Short, stiff buildings have a really fast wobble, a short period. Tall, flexible skyscrapers, they have a long, slow one. And on the vertical axis, the graph just shows the absolute maximum acceleration that building's going to feel.
And this is where the genius comes in. Instead of running thousands of super complex simulations for every new building, an engineer can just look at this curve. They figure out their building's natural period, they find that spot on the chart, and boom, it tells them the peak force they need to design for. It's an incredible shortcut that boils down decades of seismic data into one powerful tool. So let's take a walk along this curve. We'll start all the way on the left. This is where you find your short, stout buildings, like a two-story concrete structure. They have a super fast wobble, a very short period. And because they're so rigid, they pretty much just move with the ground. The main thing they feel is just the raw acceleration of the earth shaking beneath them. They're basically just along for the ride. Okay, now we move along the curve and we hit this big flat top, the peak of the graph. This is the danger zone. This is where a lot of our common, everyday, mid-rise buildings live. Their natural wobble speed just happens to line up perfectly with the frequencies in an earthquake, and that causes them to resonate. It's just like pushing a kid on a swing at the exact right moment to make them go higher and higher. The forces here, they're at their absolute maximum. And finally, way over on the right side of the curve, that's where we find the giants, the tall, flexible skyscrapers. They have a long, slow, lazy wobble. Now, you might be surprised to see that the peak force they feel actually starts to go down. The earthquake is just shaking too fast for the building to keep up. But here's the trade-off. They experience huge displacements. We're talking swaying several feet at the top. So for these buildings, managing all that movement becomes the #1 job. But here's where it gets even more interesting. A building doesn't just wobble in one simple way. Oh no, it has a whole collection of what we can call its dance moves, and engineers have to account for pretty much all of them.
You see, a building's main move is that back and forth sway, like a pendulum flips upside down. We call that its first mode. But it can also bend into an S shape or twist around its center. And the crazy part is, in a real earthquake, it's doing a little bit of all of these things at the exact same time. Each one of those behaviors is called a mode shape. And this isn't just some fun fact for a trivia night. This is serious business. Engineering codes, like India's IS 1893, actually have a rule for this. They say your analysis has to capture enough of these dance moves to account for at least 90% of the building's total mass in motion. This makes sure that no sneaky, significant vibration gets missed.
And that is exactly why this method is such a massive leap forward. Those older, static methods, they really only look at the building's main wobble. But the response spectrum method accounts for this whole complex combination of modes. It gives engineers a way more realistic picture of the stresses inside a building, which is absolutely critical for anything tall or oddly shaped.
So, how do engineers actually do this? Let's quickly walk through the recipe for safety And don't worry, we're not going to get bogged down in the heavy math. We're just focused on the logic.
The whole process follows a really clear path. First, you build a digital twin of the building in the computer. Then, the software figures out all those unique dance moves, or modes. For every single one of those modes, the engineer goes back to that response spectrum curve to find its individual peak force. Then comes the really clever part, combining all those forces. And finally, you do one last check against a trusted baseline, just to be safe. Now, the key to combining those forces is realizing you can't just add them all up. I mean, why not? Well, because the chances of the peak sway, the peak bend, and the peak twist all happening at the exact same millisecond are practically zero. So engineers use statistics, like this square root of sum of squares formula, to figure out the most probable maximum force you'll see when they're all combined.
And that brings us to the final, and you know what? Maybe the most important step in this whole process. This is the critical reality check. It's a safety net that's built right into the system to make sure that our new, fancy methods are still grounded in proven principles. And here it is. The code says that the final force you calculate with this sophisticated dynamic method has to be at least 80% of the force you would have calculated using the older, simpler, but time-tested static method. So what does that mean? It means if your fancy dynamic analysis ever spits out a number that's a little too low, a little less conservative, you are required to scale everything back up to meet that baseline. It's basically a trust but verify system, and it guarantees that as our methods get smarter, we never accidentally sacrifice safety.
Okay, so let's pull back and look at the big picture here. Why does taking a deep dive into an engineering method like this actually matter to all of us?
Well, this table really says it all. The old static method, it's fine for simple, regular, low-rise buildings. But for the tall, complex, sometimes weirdly shaped structures that make up our modern cities, ignoring those other dance moves just isn't an option. The response spectrum method gives us the accuracy we absolutely need.
And believe me, this isn't some abstract theory from a textbook. This is the workhorse of modern structural engineering. It's used for the high-rise you might work in, the long-span bridge you drive across, and all the critical infrastructure, like power plants, that our society truly depends on to stay safe and functioning. So in the end, the response spectrum method is an incredibly powerful tool. It gives engineers this elegant, reliable snapshot of the absolute maximum punishment a building might have to take. But it is just a snapshot of the peaks. What if we wanted to see the whole movie? What if we wanted to simulate a real earthquake from start to finish and watch how the building reacts second by second? Well, that, my friends, takes us to the next level of analysis. And that's a story for another time. Thanks for joining me.